for more homework. That's doing all this best. Okay, it's that time of the morning, so we're going to go ahead and get started. I have several announcements to make to start off, and then we're going to get into today's material. I'm going to try to do most of this in order of when it's going to happen, even though it's not listed that way here. The very first thing I wanted to mention is today's lab is the thermochemistry lab. As part of preparation for the lab today, you were asked to watch 2 videos. One of them dealt with the actual procedure, which is very, very easy. And then the other one dealt with the calculation in specific. So what my plan is today is we're going to start the lab with me doing another, me working through the example of the calculations. They're actually pretty straightforward for the most part. You've got a lot of the skills already, which is a limited reactant portion. You just need the Q is equal to M hat and Q of the system is equal to Q of the surroundings. So I plan to go over those calculations today because the lab is fast. The actual procedure, you'll probably be done in like 20, 30 minutes. Which means that there is plenty of time to do the four sets of calculations associated with this lab. So I thought maybe we would just go ahead, if I gave you the example that you have on the video, and if I do another example, then hopefully you can do those 4 calculations and go ahead and turn it in today. That way, all the labs that I need to grade are in my hand. And so I can get them graded and you can have a pretty good idea of where you stand ultimately in this course. So that's the plan for the thermal lab. The second thing I wanted to mention is the bonus opportunities. Again, you do have 2 bonus opportunities. One of them is tonight at 7 p.m. There is going to be it's called Conversations with Chemists through the local section of the American Chemical Society, and the speaker is Casey Thurber, who is a graduate of UCA. The link is in your bonus folder. The other bonus that is coming up is Monday by 3 p.m. If you wish to donate food to the food pantry, you can donate up to 10 items. You bring in the sheet of paper with your name on it, so I know who to do what, and I will add that to your bonuses. Okay, so that leads me into homework number 20. You will have a homework over the material we're going over today, and it will be due on Monday at 11:59 p.m. You will have a quiz over the information from this week, which is going to include the molarity calculations. It's going to include the precipitation reactions and electrolytes that we're going to be discussing today, as well as, I hope, the acid-base neutralization reactions. So that's going to be a quiz on Tuesday that will be due on Tuesday. Now, if all goes well, I will have completely covered all of the information associated with that reactions lab we did 2 weeks ago. Well, 3 weeks. That we did in the past. So I think, so basically it's going to be due on November 28th. That's the Monday after we get back from the Thanksgiving break. And it's turned in through active, so it'll be an automatic grade, and then I'll have to go in and add up all the videos into that grade to get you the final reactions lab grade. The other thing that will be due on November 28th is homework number 21. And it will be over the redox reactions that we cover on what I think we're going to cover at least on Tuesday. The last thing that I wanted to mention is the gas law lab on the Thursday after we get back. I just wanted to remind you that that will be a lecture rather than lab, and your entire lab grade is based off of attendance of the lecture. Because it takes about an hour and 15 minutes, an hour and 30 minutes, and I'll cover the entire gas law lab or gas law chapter because I only cover the parts that we use frequently. Any questions? Folks, other than your exam and maybe a homework or two in there, this outlines everything that is left of the semester. Which brings me to my last point. On Friday, I am going to try to put up all of the week's folders for the rest of the semester. That means that you're going to have to, when you go in to see what's going on, you got to look for the actual week of and make sure you get the correct week, because I'm going to try to put them all in so that you have all the information for the rest of the semester on Friday. It feels weird that we're closing down the semester. I feel like I just met you. And here we are finishing it up. Any questions for me? Okay. Then we are going to get started into the information. And I am going to pick up where I left off on Tuesday, which I'm double checking where that was. Okay, I got through the So on Tuesday, since it is associated with what we're about to talk about, we started talking about electrolytes. Electrolytes could be divided into strong electrolytes, weak electrolytes, and non-electrolytes. When we call something by strong electrolyte, weak electrolyte, or non-electrolyte, we're talking about how well it dissociates. In our case, specifically in the solvent water. And for the strong electrolytes, if you have a soluble ionic compound, it's going to be a strong electrolyte, so it's going to dissociate entirely. If you have a strong acid, it is a strong electrolyte, so it's going to dissociate entirely. We use a normal arrow for those types of reactions. For a weak electrolyte, what you have is you only have partial dissociation. And that, if you go into college chemistry too, you're going to find out that that partial dissociation really is based on its equilibrium constant. And those things that are only partially dissociate are going to be your insoluble ionic compounds. Those are the compounds that pretty much stay as a solid. Weak acids and weak bases. Because they only partially dissociate, we actually use an equilibrium arrow in our reactions, which is that double-headed arrow. And then a non-electrolyte does not dissociate at all in water. Those are typically most of your covalent molecules. That is going to be, that's the big category there. Now, to determine whether an ionic compound is soluble or insoluble, that's where you use the solubility rules. And again, you will receive these solubility rules on your exam. Those solubility rules I gave you on Tuesday. And I said the two most important rules are going to be the the first rule and the second rule, which is group 1 and ammonium compounds dissociate entirely with no exceptions. And then acetates, perchlorates, nitrates, bicarbonates, they tend to dissociate entirely. Most of your halides do, with a few exceptions, and most of your sulfates do. Then we got into the insoluble, which would be your weak electrolytes, which would be solids in solution, and basically oxides, hydroxides, sulfides, phosphates, and many more. They tend to fall into that category. And when you get into that, you have a few exceptions with the oxides and hydroxides, and actually all of the exceptions for the oxides and hydroxides are your strong bases. And then you have, for all other ions, group 1 and ammonium. So then I went on to talk about the strong acids and strong bases. There are 6 strong acids, and folks, while I'll give you the solubility rules, I will not give you the names of the strong acids. You have to know these. You have to have these 6 memorized. That's HCl, HBr, HI, HNO3, HClO4, and H2SO4. The most common mistake I see students make is they want to include HF into that category. HF, though, is a weak acid. And what's sad is, even though it's a weak acid, it is the nastiest of acids with respect to a person's body. And then you had your strong bases, which were your group 1 hydroxides, calcium hydroxide, barium hydroxide, strontium hydroxide. Again, folks, if you go back and look at your solubility rules, though, these are the exceptions to the solubility rules. So those are your strong bases. Any questions? I wanted to remind everybody because we're going to be building on these facts today. Okay, so let's go back up to today. And let's get going. So what I have discussed so far, we were talking about the solubility rules, and when we were talking about the strong acids and strong bases, we primarily were focused on the strong electrolytes. The only part of Tuesday's lecture where we got into any of the weak electrolytes were the insoluble compounds in the solubility rules. But if you look at the weak electrolytes where I was describing them, I said it was going to be your insoluble ionic compounds, it's going to be your weak acids, and it's going to be your weak bases. So we talked about the insoluble ionic. Now we need to discuss who are the weak acids, who are the weak bases, how do you recognize them, and what are their states of matter when you see them. So the first thing we're going to talk about are going to be your weak acids. And folks, this is where it gets a little bit confusing, because your weak acids still will have the state of matter of aqueous. Now, to recognize a weak acid, recognize. What are you going to look for? Your weak acids tend to start with hydrogen, the formula, I should say. Or it will contain a COOH group. Folks, this COOH group, as you will learn in organic chemistry, and maybe some of the others, is called the carboxylic acid. Group. Now, as far as who is the acidic hydrogen, when a compound starts with hydrogen, it is telling you that's the acidic hydrogen. So when the compound starts with hydrogen, that's the acidic hydrogen. Now, when you have a carboxylic acid group, the acidic hydrogen is the hydrogen attached to the COO. And what we mean by acidic hydrogen is we mean that is the hydrogen that is going to dissociate from the rest of the compound. Knowing who the acidic hydrogen is going to be important when we get into acid-base neutralization reactions. And it's going to be extremely important when you get into college chemistry too. Not right off the bat, but about halfway through, a third of the way to halfway through the semester. Okay. So the other category I mentioned was the weak base. Again, the weak bases will have the unit of aqueous if it dissolves in water. But what are the weak bases? You will recognize them because their formula will have an NH group. Now, this could be NH3, which is our most common, which is ammonia. Ammonia. It could be an NH2 group. It could be an NH group. And technically, it also can be an N group where you don't actually have any hydrogens attached to it. These compounds are referred to as amines. Now, many of you have gone through one or more biology classes, and you have heard the term amino acid. If you look at an amino acid, has by itself usually a NH2 group attached to a carbon with a double bond. No, getting them wrong. Carbon attached to a hydrogen with an R group of some sort. We call R group anything. So it could be a carbon chain, it could be a hydrogen, it could be just anything. Attached to a C double bond O OH group. It is called an amino acid because it has an amine and it has a carboxylic acid. And these things tend to react together. Now, we're not going to do anything with the the amino acids. I just wanted to tell you that these acids and bases that we're talking about, you've actually seen them. They just may not have specified them as an acid or a base. Questions? Okay. So what I want to do is I want to take a minute to go over. So let's talk about our strong electrolytes a little bit more and what it means. And as we do, what we're doing is we're going to be developing what is called a dissociation reaction. So what does it mean? Okay, so let's take one of our soluble, or a couple of our soluble ionic compounds. And we have a soluble ionic compound, such as sodium chloride, and that sodium chloride is placed in water, hence the term aqueous. Then what it means is that the sodium chloride is going to completely dissolve into sodium ions in water. And chloride ions in water. If you have zinc nitrate Because it is soluble, it will be aqueous. And what it means is that that zinc nitrate is going to dissociate to form zinc ions and 2 nitrate ions. Folks, the entire key to this is if I were to actually be able to take a beaker of zinc nitrate and I were to be able to take and zero in and actually look at individual atoms, ions, molecules, if I had that capability to see one, I wouldn't see this. This doesn't exist in water. What I would see is this in that beaker. This doesn't exist in water. It's not in a compound in water. It only exists in this form. If you could actually go in and peer in, you would only see the zinc and the nitrate present, not zinc nitrate. With your acid base or your strong acids, let's take hydrochloric acid. Again, its state of matter is aqueous because it is an acid. If we were to take and really look at it, we would not see HCl combined. What you would see in solution is you would see a proton and you would see a chloride ion. For sulfuric acid, you would not see sulfuric acid. You would not see an H2SO4. You would see 2 hydrogen ions and 1 sulfate ion for every H2SO4 that was added. This is what we mean by strong electrolyte, because remember, an electrolyte conducts electricity if there are free floating ions. Your strong electrolytes, again, you don't have this. You have only ions in solution. That's why they're called a strong electrolyte. It's because you have a ton of ions in their compound. Now, when you get into a weak acid, a weak electrolyte. Remember, it only partially dissociates. In this particular case, the degree of dissociation is based on the substances equilibrium constant, which we're not going to talk about, but that is what it is based off of. And it just so happens that weak electrolytes have very small equilibrium constants. So that means they don't dissociate very much. Now, So let me give you an example. If you were to take silver chloride and add it to water, the silver chloride is not going to dissociate to any great extent. So there's essentially no reaction when you add silver chloride to water. In reality, there's a tiny amount, but it's essentially no reaction. If you were to add manganese phosphate to water, essentially there's going to be no reaction. Again, there's a little bitty amount, but there's essentially no reaction. So our insoluble ionic compounds, if you just add those to water, you're going to get essentially no reaction. Your weak acids, such as acetic acid, acetic acid, there for now we're going to say is no reaction. In reality, folks, all of these, there's a tiny amount of reaction or a tiny amount of dissociation. It's just not a grand amount. Compared to HCl, there is no reaction with acetic acid in water. Same thing with your weak bases. If I were to add methylamine, I would say it's aqueous, but there's essentially no reaction. Questions? So when we say strong electrolyte compared to weak electrolyte, we're basically describing, in the case of strong electrolytes, if I were to peer in, all I would see would be ions. In the case of your weak electrolytes, if I were to peer in, depending upon the equilibrium constants, I might see a little bit of ion, but I'm going to see mostly the compound. That's what we're getting at. Is if you take a weak electrolyte and you were to be able to peer down into it to see what's really there, you would see a little bit of ions. But for the most part, you would see compound. Questions about that concept? Because it's the driving factor into the next pieces. Same thing with some non-electrolytes, there would be no reaction. Now, I said it's the driving factor into the next pieces. The next piece is we're going to talk about the 3 types of equations or reactions. One of them, the first one you're already familiar with, that is going to be the molecular reaction. The molecular reaction shows the substances as compounds. shows all the substances in the compound form. Now, the second type is going to be the complete ionic reaction. And this shows us how things actually appear in solution. To go from molecular to complete, you're going to break the strong electrolytes, which I am going to shorten as SE, the strong electrolytes into ions. The third form is going to be the net ionic reaction. And the net ionic reaction shows what undergoes a change. During the reaction. You get to the net ionic reaction from the complete ionic reaction by removing the spectator ions. Where your spectator ions are ions that appear the same on the reactant side and the product side. I'm going to your lab now because we're fixing to do this. If you don't have your lab, you can write it on paper, but if you do, it's a good place to go. Because everybody will have to turn in their own this time, since it's done on active. You don't turn in the packet, you just turn everything in on active. Okay, so experiment number 1. You began with a small strip of magnesium solid. And you combine that with hydrochloric acid, which was aqueous. This is an example of a single displacement reaction. Now, the reason I know it's single displacement is because I started with an element and a compound. That's how you know it's single displacement. You start with an element and you start with a compound. So this is also going, what I'm about to describe is also going to fit with the steel wool and copper sulfate one. So both of these, I'm only going to do one of them, you get to do the other. But the concept is going to be the same. As the steel wool with the copper sulfate. I'll give you a little bit of hint on the steel wool copper sulfate, but it's the same process. What is single displacement? In a single displacement, the element, in our cases, will replace the cation in the compound. Cations are just positively charged ions. So in other words, we started out with magnesium solid and our hydrochloric acid. What is going to happen when we go to the product side is the magnesium will be combining with the chlorine and you're going to get hydrogen by itself. Now, you got to go back to what the ions are. What is magnesium as an ion? When it combines in an ionic compound, what is its form? It's charged, but what's the charge? 2+. And what's chloride's charge? -. So the compound that it would make is MgCl2. And what form does hydrogen take when it's all by its little lonesome? H2. Now, if you will recall, when you did this experiment, what did you observe? We saw effervescence, bubbles, bubbles. Now, which of these two compounds is likely to be bubbles? H2 is likely to be the bubbles, and bubbles are gas. Now, for the other one of these, we're going to have to determine it using solubility rules because this is an ionic compound. So we're going to use the solubility rules to determine its state. According to rule number 3, halides are soluble except for silver plus, lead 2+, and mercury 2+. This isn't one of the exceptions, so it follows the rule. So this one is going to be aqueous. Balancing this equation, you got to always balance it. And to balance it, you're going to need 2 hydrochloric acids. Folks, this is your molecular reaction equation. Solubility rules. And according to rule number 3, your halogens are soluble with the exception of lead 2+, silver plus, and mercury 2+. So those are the only 3 that will be a solid. The rest will all be aqueous. Okay, now I said to get from the molecular to the complete, you've got to dissociate anything that's a strong electrolyte. Folks, All of your strong electrolytes were aqueous. So they're the only ones you're going to have to even question. You don't have to question solids. You don't have to question gases. You don't have to question liquids. You only have to ask yourself about the aqueuses. Are they strong electrolytes? So hydrochloric acid, is it a strong electrolyte or weak electrolyte or non-electrolyte? Strong, why? Because it's a strong acid. Magnesium chloride, is it a strong electrolyte, weak electrolyte, or non-electrolyte? Strong, because it is a soluble ionic. Now, if you look at what I said about your your complete ionic equations, we're going to take the strong electrolytes and we're going to break them up. So to get to our complete, we're just going to bring magnesium solid down. But we are going to have to break up the hydrochloric acid. The hydrochloric acid, the ions are H plus and Cl minus. The ions will have the same state of matter as their parent compound. And when you have a coefficient, the coefficient is distributed across both, or however many ions you have. So that 2 is distributed to both the hydrogen and the chloride. On the product side, we got to break up our magnesium chloride into its ions, which were magnesium ion and chloride ion. The ions will have the same state of matter as their parent compound. But we have a subscript on the halogen in the magnesium chloride. Anytime you have a subscript, and that subscript is there in order to make the compound charge neutral, that subscript becomes a coefficient in the complete ionic. Anytime you have a subscript, and that subscript is simply there to make this compound charge neutral, then it becomes a coefficient in the complete ionic. So we would have to put it as 2 chlorides. And then the H2 we simply bring down because it's not an electrolyte. Folks, another reason I do this right here, where I go, okay, I'm going to have to combine the magnesium with the chlorine. The reason I do this is you will notice that that happened to be the same thing I brought down later on. And it makes it obvious that that 2 had to become a coefficient. Now, and yes, folks, when you write a complete ionic, you've got to show the elements, the charges, if it's charged, the state of matter, and you've got to put it in the coefficients. If you miss any one of those pieces, it will be wrong. Now, to get to the net ionic. Once you get the complete ionic, the net ionic's a breeze. Spectators appear the exact same on both sides of the equation. On the reactant side, you had 2 Cl minuses aqueous. On the product side, you have 2 Cl minus aqueous. They look identical because they have the same element, the same charge, the same coefficient, the same state of matter, It's identical. So those are spectator ions. To get to the complete ionic, I'm going to eliminate those spectator ions and just bring everything else down. And that is the complete ionic. We're going to have to come back to the first one after we talk about the next, after we talk about stuff on Tuesday, because we haven't gotten to the redox side. So what you should be able to do now, and here's what I would recommend. Over the weekend, I would recommend that you work on. If I can get to it, it would be nice. Experiment number 7's molecular complete net ionic equation. That way you can ask me questions as to whether you have it correct before you have to turn it in. Because I'm going to leave number 7 up to you. It's going to be very similar. Now, I will tell you that as far as the iron is concerned, when it makes an ion, it's going to make an iron 2+ ion. But the rest of it, I want you to do on your own. And we're going to move on to experiment number 2 now. Experiment number 2. You started with PbNO32 and Ki. The PbNO32 was a colorless solution. The Ki was also a colorless solution. Now, this is an example of a double displacement reaction. In a double displacement reaction, basically, the cations swap their anion partner. So and this is how you got to work this, folks. You cannot just simply pick things up and move them. You can't do that. You got to go back to their ions and figure out what the compound really is. So the way you have to do this is go, okay, I thought midnight, I got this PbNO32. What is the cation of PbNO32? Pb what? 2+. What is the anion in PbNO32? NO3, and what's its charge? -1. In Ki, what is the cation? Potassium, what's its charge? +1. In Ki, what is the anion? I-. That's how you have to ask yourself these questions, folks. Now, what is the formula for a compound that has Pb2 plus and I minus? I saw somebody mouth it, PbI2. What is the compound with the formula of K plus and NO3 minus? KNO3. Folks, notice I didn't just pick up the NO3 too and move it over. You can't do that. You've got to go back and ask those questions. Now you balance it. To balance this equation, I'm going to need 2 potassium iodides, 2 KNO3s. Now we have to figure out the states of matter. These are both ionic compounds. So where do I go to determine my states of matter? Solubility rules. PbI2. Okay, I'm looking at the I because other than rule number 1, it's all about the anion. I2. I is iodide. So I'm looking at rule number 3. Your halides are soluble except Hg plus, Pb2 plus, and Hg22 plus. This is one of those exceptions. So it does not follow the rules. So this one is a solid. KNO3. Whether I want to look at the potassium, rule 1, or the nitrate, rule 2, they're both soluble all of the time, no exceptions. So that's AQ. That, folks, would be your molecular equation. Now, we need to dissociate this stuff. And who do we dissociate from the net ion, from the molecular to the complete ionic? Well, that's who we look at as the aqueous, but who specifically? Strong electrolytes. So we got to determine who's a strong electrolyte. Now, it's really quite easy with ionic compounds because if it's soluble, it's strong. If it's aqueous, it's strong, in other words. So since this is an ionic compound, it's a soluble ionic compound, which means it's a strong electrolyte. The next one is a soluble ionic compound, so it's a strong electrolyte. And KNO3 is a soluble ionic compound, so it's a strong electrolyte. Again, you don't have to worry about solids, liquids, and gases. You only have to determine whether the aqueuses are strong, weak, or non. What that means is I'm going to have to dissociate my lead nitrate. I'm going to have to dissociate my potassium iodide, and I'm going to have to dissociate my potassium nitrate when I get into the complete ionic reaction. Now, folks, this is another place where asking these questions comes in handy. These are the ions that were on both this side and this side. These are your ions, folks. So when I break lead nitrate apart, it's going to break apart into Pb2 plus and NO3 minus. The ions will have the same state of matter as the original compound. But the fact that we had NO3 2, that 2 is simply there in order to make this compound charge neutral, so it becomes a coefficient in the complete ionic. In our next compound, the ions are K plus and I minus. The ions will have the same state of matter as their parent compound. The fact that we had a coefficient of 2 means that that 2 needs to be distributed to both of the ions. Sorry, it is because I'm having to crowd this all into one line. So it reads so far, Pb2 plus aqueous plus 2 NO3 minus aqueous plus 2 K plus aqueous plus 2 I minus aqueous. That's what it reads so far. Now going to the product side, you just bring down anything that's a solid, liquid, or a gas. So we're going to bring PBI2 just as is into the complete ionic reaction. But now we've got to break apart the KNO3. The ions for KNO3 were K plus and NO3 minus. The ions will have the same state of matter as their parent. The fact that the coefficient is a 2 means that you're going to have 2 potassium and 2 nitrates. So the product side is PBI2 solid plus 2 potassium ions plus 2 nitrate ions goes to make, and the potassium and the nitrate are, the potassium and the nitrate are aqueous. This is your complete ionic. Your net ionic gets rid of spectators who looks identical on the reactant side as they do on the product side. Nitrate, I heard, and the potassium. So to get to the complete ionic, the net ionic, I'm just going to bring in everything that is left after getting rid of my spectators, because the only thing that underwent a change is the lead and the iodide. Went from aqueous to solids. Questions? Another one you may want to do over the weekend now is number 8. That way I can check it for you if you want before you have to turn it in, because it is identical to what we just did. I'm trying to help out some. Yes.
I guess I don't understand. Would this be the same exact reaction if it were the net reaction as well?
Technically, what you saw, first of all, these are just there to counterbalance the charges to begin with. This is what you saw that turned yellow. This is the reaction.
Okay.
You made this lead iodide, which is yellow. Okay. Folks, the next thing we're going to talk about is acid-base neutralization. And acid-base neutralizations are also double displacement reactions. And we're gonna work on number, I don't know, it's number 5. That's what we'll be doing next. Again, it means we swap cation and anion partners. Now, the neat thing about double displacement reactions that are acid-base neutralization reactions, though, is that you will always have an acid and it will react with a base. And for the double displacement reactions we will be doing, for the acid-base neutralization reactions we'll be doing, one of your products will always be water in liquid form plus an ionic salt, which is basically nothing. It's just another name for an ionic compound. So in the case of HCl, which is aqueous, reacting with sodium hydroxide, which was a clear colorless solution, it went to form water as one of the products. What is the other? Huh? It's a salt of NaCl. I think you said that the first time, I just didn't hear it. And you may wonder how this is a double displacement reaction. If you go back and look at, if you tear this apart and look at the ions, like I suggested you do, what is the cation? Go away. What is the cation in HCl? H in what form? H plus. What is the anion in HCl? Cl minus. What is the cation in NaOH? Na plus. And what is the anion in NaOH? OH minus. In other words, water is just H plus OH minus combined. So it's still a double displacement. Now you got to determine what the state of matter is of the salt. And what is the state of matter of this salt? It is aqueous. We know it's aqueous for a couple of different reasons. Number one, it is a soluble ionic compound. So that's one reason. If you look at your solubility rules, it follows the solubility rules. But the other reason you would know it is if you look at your appearances, you had a clear solution at the end, which means there was no solid present. Now to take this down, we got to break apart all strong electrolytes. Well, since NaCl, we've already said is soluble ionic, it's got to be a strong electrolyte. What about HCl? It's a strong electrolyte. Why? Because it's a strong acid. What about sodium hydroxide? It's a strong base, or you could say it's a soluble ionic, and so it's a strong electrolyte. So when you go to the go from the molecular to the complete, we're going to have to break up everything but the water into its ions. which you've already done, the hard part. So the HCl, H plus, and Cl minus, they're both going to have the same state of matter as their parent. Sodium hydroxide, you have a sodium ion and hydroxide ion. They're both going to have the same state of matter as their parent. That goes to make water. Water being a pure liquid, you just bring it down. And sodium chloride, it's going to be sodium ion and chloride ion. Which is going to have the same state of matter as their parent compound. This would be your complete ionic equation. Now to get to the net, we remove spectators. Your spectators are the sodium and the chloride. So the net ionic equation is H plus OH minus goes to form water. One thing I will let you know for future reference, this is always the net ionic for a strong acid, strong base reaction. Either one. You're not going to have to answer that on the active. So basically what I've done is, yes, I've only given you 3 examples and worked through 3 of your problems, but you should be able to work through an additional 2 now. And other than the redox. What we're going to do on Tuesday is we're going to pick up with this concept of the acid-base neutralization, because I've only shown you strong acid, strong base neutralization reactions. I need to show you weak acid, strong base neutralization reactions. We're not going to do a weak base, but I do want to show you strong acid, weak acid, strong base neutralization reactions. And then we're going to get into redox on Tuesday. And once we do that, you should have all of the components necessary to finish the lab. I will see everybody in lab today. And I know there's like 30 problems of homework, so don't wait until the last minute to start it. Some of it's fast, some of it's going to be slower. It'll give you a lot of practice with this stuff. I'm going to my office now, and then I'll be going back to I only have X period otherwise. What's that?
I got the.
Oh, you can either bring it now or during X period.
Okay, thank you.
So whichever.
Is the Zoom count as 6 minutes? Because I have a family friend coming in. She's just traveling through it. She's staying Monday night. And I was wondering, but if it doesn't count as 6 minutes, I was gonna.
For class?
Yes.
Yeah, it should be fine.
Okay, thank you.
Yes.
So can I bonus point? Can we bring the form to you, or do we give it?